Hello, AP Chemistry class. Today we're going to talk about acids and bases, and this is going to be the part 1 of this lecture. You get part 2 next week and part 3 the week after that, right before the exam. So when we're looking at acids and bases, we're going to talk about quickly the definitions and then go into some of the chemistry involved with acids and bases and some of the calculations involved. So first, let's look at this. What is an acid? Let me get my pen. No, that's my laser pointer. All right, let's do it this way. There we go. So we're going to look at two definitions of acids. We got two definitions. One is the Bronsted-Lowry. And this is the one everybody kind of knows. And this is when an acid is a proton donor. And a base is a hydroxide, OH minus, donor. And we're going to work with Bronsted-Lowry definition for most of this chapter, but there is another definition I want you guys to realize, and that is Lewis acid and base. All right, Lewis acid is a compound that accepts an electron pair, usually a lone pair. And a base is a compound that donates the electron pair. Now, to be honest, there's probably about 7 different types of definition based on what type of chemistry you're looking at. And the Bronsted-Lowry is the most common and the one that we use the most often, and it explains about 90% of all the chemistry that we have if it's involved in acid and a base. The Lewis acid and the base incorporates the next 5 to 7%. It's common, and it helps explain some unique chemistry that involved when you get into college. And the other 5, it depends on which branch of chemistry you're working on and how specialized you're going to get. So you get those different 5 later when you go to if you go to graduate school. So okay, we're not going to cover those. So let's look at some more definitions. So if we come here and there are the acids and bases can be divided up as strong or weak. A strong acid or base dissociates completely. And we'll talk about that chemistry a little later on, and we're gonna show you those. We're just going over the definitions right now. Weak acid and base. Slight dissociation. That means the compound actually dissolves in solution in water, and then a little bit dissociates. So we have an equilibrium process. The acid goes in, dissociates, and goes back again. So this is what I mean by slight dissociation. And actually, as I'm thinking about this, let's talk about some more definitions. The word conjugate means the that's a U. What we talk about conjugate is how is something that's related to another compound, and we usually minus a hydrogen or add an OH to it. So conjugate is, for example, we have a conjugate acid and a conjugate base. And this is a kind of hard word to define chemically, so I'm just going to show you. So we're going to have HCl, and that's going to dissociate to H plus, and let me add water to this. So this is going to be H3O plus Cl minus. This is my acid. This is my base. This is the conjugate acid, and this is the conjugate base. Now this is actually used as the Lewis acid base definition, but it works well with some other for the weak acid, which I'm going to show to a minute. So the acid is related to the conjugate base by the absence of the H plus, and the base and the conjugate acid are the same, but we just have this as an H. So this is what we mean by conjugate. It's always the product. You guys need to know this because this is going to influence everything in acid-base chemistry. Now, if we have a weak acid base, say we've got acetic acid, CH3, CO2H, plus H2O. We're going to get CH3, CO2 minus, plus H3O plus. This is a weak acid. We got mostly this, but some of it will dissociate to form this. This is my acid. This is my base. This is my conjugate base. And this is my conjugate acid. So there is a relationship between the conjugate base and the acid, and the conjugate acid and the base. Remember, the conjugate means it's the product. So if I flip this around, have H3O plus my acetate anion, H3O will be the acid, and the conjugate and the acetate ion will be the base. And then my conjugate acid will be acetic acid, and my conjugate base will be water. So it depends on which side you're looking at. So let's go to my next empty slide. So when we're looking at strong acids and bases, I'm going to focus on them first. So strong acids, the common ones are called mineral acids also. And I don't know how to spell, so let me erase that. All right. There we go, mineral acids. And the common ones are HCl, HBr, HI, See a trend? These are all the halogens. Hydrogen chloride, hydrogen bromide, everything in water become an acid. Nitric acid, HNO3. Then it gets a little bit more complicated. Phosphoric is also labeled a mineral acid, but it's both. Says you got 3 hydrogens coming off. We'll talk about this the 3rd week, but this means that hydrogen you can lose 2. It's both a strong and weak acid. Sulfuric acid is the same way. The first hydrogen comes off fairly easily. So let's focus on this. This is your common. HF, hydrogen fluoride, or hydrofluoric acid, is not a strong acid. It's actually defined as weak. So what's happening is that HCl, when we add it to water, we have this H3O plus. Now, H3O plus is equivalent to saying H plus. We can kind of use this as a shorthand version of this. In actuality, the structure of protons, of what's surrounding the protons, is actually a little bit more complicated. I'll get to that in a minute. But this is the acid we're doing this. This is the equation. This is very strong. This dissociates completely. This is too weak to pull hydrogen away from water. Oxygen is highly electronegative, more electronegative than chlorine, so it's rather going to keep that. So this is going to be, chlorine will not take the proton away, nor will it take a proton away from normal water. So this reaction will not happen. So this is what I mean by strong acid, and it dissociates completely. This is the react. This is reacts. This is very reactive. So in all of our reactions that involved an acid and a base, we're looking at this H3O plus to be part of that reaction. Now, strong base is even fewer of those. So when we talk about strong base, we're talking about like NaOH, potassium hydroxide, lithium hydroxide. You may get calcium hydroxide. But the thing is, folks, there's only not that many of these, mainly because that hydroxide precipitate, all the metal hydroxides precipitate. Most metal hydroxides are not, or I should say, are not soluble. So they don't become a base. To become a base, you've got to be soluble in the solution you're in. And so the chemistry is NaOH. Solid, and we're adding water. Water doesn't do anything. It's a solvent, so you have Na plus OH minus. This is what we usually get. And it fully dissociates. Sodium is too weak to pull off an OH from water, so it just floats around. This is the reactive component. So when we look at the chemistry of acids and bases, we focus on the NaH plus and the OH minus. So let's look at what water does. Because all these compounds are not reactive unless because we need to have water present. Water does something called autoprotolysis. I can't spell. Something like that. That means two H2Os will react, and it goes back and forth to form H3O plus OH minus, or the simple way we draw this is H2O comes back and goes OH minus and H plus. It doesn't matter how you write these. So this is what water automatically becomes an acid or a base. It does both. This is unique. One of the unique things about water. Now, also, water has structure. So once we have H plus floating, water surrounds it. Because of the polarity of the water molecule. Remember, this is slightly negative and this is slightly positive. These mean slightly. So you're going to have this proton surrounded by a whole bunch of water. And you're going to have the hydroxide surrounded by a whole bunch of water. This is how we dissolve a lot of things. Now, this is why this is reactive, because this is a strong, very small, highly positive charge. It's going to react with a lot of things. But I'm going to focus on this at this moment because we can actually set up an equilibrium for this reaction. So the reaction is H2O going to H plus OH minus. So we have this equilibrium constant, and we have the products H plus OH minus. Water is our solvent. We don't care about that, or it becomes 1. This is something very special because we have calculated Kw, and that's equal to 1 times 10 to the minus 14th. And that's equal to H plus and OH minus. And you're going to be using this equation to figure out, if I give you a concentration of protons, you can figure out the hydroxide and vice versa. Now, with this Kw, I'm going to show you that do P. P is actually a mathematical term, meaning negative log of something. So if I go Px, that means it's the minus log of X, concentration of X. So pH is defined as the negative log of the concentration of H plus, while pOH is equal to the minus log of the concentration of OH minus. Know these equations. So I'm going to go pKw is equal to, we've got 1 times 10 to the minus 14. That's going to end up being 14. This is going to be important, guys, because not only if we could do this, that means pKw is equal to pH plus pOH. Take the negative log all the way through. So 14 is equal to the pH plus pOH. Now, one of your assignments is going to be figuring out the pH of solutions and the pOH of solutions. So this is one of the relationships you can do. So review. Okay, we're going to say that we know that pH, Kw is equal to 1 times 10 to the minus 14th. pKw is equal to 14. And that Kw is equal to the concentration of H plus O times OH minus. Whoops, sorry folks, I keep touching the pen. OH minus. And that pKw is equal to 14, which is equal to pH plus pOH. So when we work today on the assignments I'm going to give you, we're going to work on figuring out the concentration of H plus, the assignments. You're going to have 1 online and 2 ALs. You're going to have determine the pH, pOH of solutions, given a strong acid and a strong base, and you're going to work with these relationships.